The planets of our solar system are familiar concepts, often learned in childhood from a simple mnemonic or a classroom poster. The list of 8 worlds orbiting our Sun, from Mercury to Neptune, has long felt settled and complete. That established model, however, may be incorrect. In 2025, a scientific team presented a mass estimate for a planet that no telescope has ever directly observed. The calculation points to a world of 4.4 Earths, following an orbit so far from the Sun that a single journey around it takes between 5,000 and 20,000 years. The last time this theoretical object would have been at its closest point to us, human civilization was either building the Great Pyramids or had not yet developed agriculture. If this world truly exists, it means every chart of the solar system we have ever seen is fundamentally missing a piece. We have all grown up with a cosmic map that omitted an object more than 4 times as massive as our own planet, a detail that went unnoticed throughout the entire history of telescopic astronomy. The trail of evidence for its existence spans 2 centuries of searching, and even involves a photograph that might have been stored in a government archive since 1983. The story is not straightforward. Its details are consistently strange. This raises the question of how we arrived at this point, and why the case for a world beyond Neptune, after 200 years of mistaken searches, continues to grow more compelling. In 2025, a team at the California Institute of Technology published a specific figure, 4.4 Earth masses, with a margin of error of plus or minus 1.1. This number represents the estimated weight of an object moving through our solar system at such an extreme distance that light from the Sun requires more than 2 days to reach it. No instrument has ever captured a photograph of this body, and no probe has ever visited its remote location. Despite this, the mass estimate appears in a peer-reviewed scientific paper, supported by NASA funding and based on more than a decade of gravitational data. Its orbital path, defined by a semi-major axis between 360 and 460 astronomical units, places it in a realm of profound cold. For perspective, 1 astronomical unit is the distance from the Earth to the Sun. An orbit at 380 astronomical units is approximately 10 times farther out than Neptune. Its orbital period is estimated to be somewhere in the vast range of 5,000 to 20,000 years. This timeline suggests that if the planet is real, it last passed through the inner part of its orbit around the time the Great Pyramid at Giza was being constructed, or perhaps even earlier. The Caltech researchers did not announce their findings at a press conference. Instead, they published refined calculations that updated a model they first put forward in 2016. These refinements provided a narrower estimate for both the planet's mass and its likely orbit. Their work incorporated new information from distant, icy objects whose trajectories through space behave as if a significant, unseen mass is gravitationally influencing them. By the standards of the outer solar system, a mass of 4.4 Earths is relatively small. Neptune, for instance, is equivalent to 17 Earths, and Uranus is 14.5. Yet, a world of 4.4 Earth masses would still be substantial enough to be the dominant gravitational force in the far reaches of the solar system. It would be massive enough to shape the orbits of smaller bodies, capable of tilting and arranging them into configurations that should not naturally occur without an underlying cause. The evidence is entirely indirect. Every piece is derived from observing other objects and carefully measuring their motion. This technique is known as gravitational inference, and it is the same method that successfully led to the discovery of Neptune back in 1846. At that time, astronomers had noted that Uranus was deviating from its predicted path. They calculated where an undiscovered planet would have to be to create the gravitational pull responsible for these anomalies. When they aimed a telescope at that precise location in the sky, they found Neptune. The Planet 9 hypothesis is built upon the very same logic. A collection of distant objects beyond Neptune's orbit exhibits a strange clustering that cannot be explained by probability alone. Their orbits seem to share similar orientations, and their orbital planes are tilted in a similar fashion. The most direct explanation for these alignments is the presence of a single, massive body orbiting far from the Sunday. Such a planet would, over immense timescales, gently guide these smaller objects into a kind of gravitational formation. The Caltech team has dedicated years to constructing this argument. Konstantin Batygin, a theoretical astrophysicist, focuses on the complex orbital mechanics, while Mike Brown, an observational astronomer, leads the physical search for the object. Their collaborative work has resulted in multiple papers that have steadily refined the predicted mass, orbit, and location of this unseen world. The broader scientific community has taken notice. Major survey telescopes are now allocating observation time to this search, the Vera-C. Rubin Observatory in Chile, once it becomes fully operational, is expected to scan the southern sky with sufficient depth and frequency to detect a planet at 400 astronomical units, if one is there. The concept of a Planet X, a hypothetical world beyond Neptune, has a history stretching back over a century. It is a history marked by incorrect assumptions, flawed calculations, and one remarkable coincidence that misled the entire field of astronomy for 76 years. The current hypothesis, however, is founded on superior data and more sophisticated mathematics than any of its predecessors. But being better does not make it certain. What follows is the story of that long search, a narrative of mistakes, debates, and the persistent accumulation of evidence that resists every attempt to be explained away. Percival Lowell was born in 1855 into one of Boston's most prominent families. His brother, Abbott Lawrence Lowell, would become the president of Harvard, and his sister, Amy, would posthumously win a Pulitzer Prize for her poetry. Percival Lowell, for his part, developed an intense fascination with Mars. In 1894, he financed the construction of an observatory in Flagstaff, Arizona, situated at an altitude of over 7,000 feet, for the specific purpose of studying the red planet. He became convinced that the dark lines observed by Giovanni Schiaparelli on the Martian surface were in fact canals, vast, engineered waterways that he saw as proof of an intelligent civilization struggling to survive on a drying world. He authored 3 books on the subject, delivered public lectures to packed auditoriums, and meticulously drew elaborate maps of these canal networks, complete with junctions he named oases. The scientific establishment remained deeply skeptical. Other astronomers, using telescopes of comparable power, were unable to see the canals Lowell described. Many suspected the lines were merely optical illusions, a product of the human eye's natural tendency to connect separate, faint features into coherent patterns. Edward Barnard, working at the Lick Observatory with a larger telescope and under better atmospheric conditions, reported seeing no canals whatsoever. Lowell was unconcerned. His personal wealth allowed him to fund his own research, and his fame ensured he had the public's attention. He was also resolute enough to completely disregard his critics. By 1906, his focus had shifted to a new obsession. The orbit of Uranus still showed slight irregularities that could not be fully accounted for by the gravitational pull of Neptune alone. Lowell believed these residual perturbations indicated the existence of another, more distant planet. He calculated it would be a massive world, about 7 times the mass of Earth, orbiting in the cold darkness far beyond Neptune. He named it Planet X, with the X signifying its unknown nature. Lowell dedicated the final decade of his life to calculating the location of this hypothetical Planet X. Using the observed deviations in the orbit of Uranus, he worked backward to estimate the mass and position of the body that must be causing them. The mathematical work was exceptionally laborious. In an era before modern computing, every calculation was a meticulous process, carried out by hand or with mechanical adding machines. Percival Lowell employed a dedicated team of human computers, who were predominantly women, to perform the immense and repetitive arithmetic required for his work. He formally published his predictions in 1915, suggesting that a world he called Planet X resided in the constellation Gemini. According to his figures, it would possess a mass similar to that of Neptune. Lowell was confident it could be located with a sufficiently powerful telescope and a systematic photographic search of the heavens. He passed away on November 12th, 1916, at the age of 61, never having found his Planet X, though he also never abandoned his belief in Martian canals. What he left behind was an observatory, a considerable fortune, and a set of predictions that his colleagues felt a duty to investigate. After his death, the Lowell Observatory carried on the search for the elusive planet. The effort was initially sporadic, as legal disputes over Lowell's estate, initiated by his widow Constance, who contested the will, absorbed both resources and focus for several years. With the observatory's funding in a precarious state, the staff nonetheless persevered. Their method involved photographing targeted sections of the sky near Lowell's predicted position. They would then compare photographic plates taken weeks apart, searching for any single point of light that had moved against the fixed backdrop of distant stars. A moving dot would signify a nearby object within our solar system. If that object was in roughly the correct location, it would mean Lowell's theory was correct. The search continued without success throughout the 1920s. By this time, the majority of professional astronomers had moved on. The supposed perturbations in Uranus's orbit were minor. The predicted planet was distant and likely very faint, and Lowell's scientific reputation, damaged by the controversy over Martian canals, cast a shadow of doubt over the entire endeavor. The observatory was in desperate need of a breakthrough. What it received instead was a 24-year-old from Kansas, a young man with no college degree but a deep passion for astronomy and his own homemade telescope. Clyde Tombaugh arrived at the Lowell Observatory in January of 1929. He was a farm boy from the small town of Burdick, Kansas, which had a population of about 400. He had ingeniously constructed his own reflecting telescope using spare parts from a 1910 Buick and a cream separator. With this instrument, he would spend clear nights sketching the planets Jupiter and Mars from his family's wheat field, a quiet pursuit after long days of farm labor. He mailed these drawings to the Lowell Observatory, simply hoping to receive some professional feedback. Instead, they offered him a job. Tombaugh was just 22 years old and had never attended college. His assignment was as straightforward as it was grueling. He was to photograph the sky along the ecliptic, the plane on which the planets orbit the Sunday. He would then compare each pair of photographic plates using a device called a blink comparator, which rapidly alternates between two images of the same star field taken on different nights. Any object that appeared to shift its position between the two exposures would belong to the solar system, while everything else would remain fixed as a distant star. Tombaugh was exceptionally methodical. He spent long hours at the telescope capturing the images, followed by even longer hours at the blink comparator, patiently scanning each pair of plates for any sign of movement. The plates themselves were dense with hundreds of thousands of stars, and most nights of work yielded nothing. But on February 18th, 1930, Tombaugh found it, a tiny dot that had shifted its position on plates taken on January 23rd and January 29th. The object was located near the constellation Gemini, remarkably close to where Lowell had predicted planet X would be. The Lowell Observatory made its official announcement of the discovery on March 13th, 1930. The date was not chosen by chance. It was the anniversary of both Percival Lowell's birth and William Herschel's discovery of Uranus. The new object was named Pluto. The name itself was suggested by an one-year-old girl in Oxford, England, named Venetia Burney, who felt that the Roman god of the underworld was a fitting name for such a cold, dark, and remote world. As a subtle tribute, the first two letters, P and L, also served as Percival Lowell's initials. The observatory officially adopted the name within weeks. The public celebration was immense, with newspapers featuring the story on their front pages. It appeared that Lowell's prediction had been triumphantly vindicated. Planet X had been discovered, and Lowell had been right all along. There was, however, a problem. Pluto was incredibly small. Initial estimates suggested its mass was roughly equivalent to that of Earth, which was already suspiciously low for a planet thought to be gravitationally influencing Uranus. Over the subsequent decades, that mass estimate continued to fall. By the 1950s, it was revised down to 1/10 of an Earth mass, and by the 1970s, it was closer to 1/100th. Then, in 1978, James Christie at the United States Naval Observatory discovered that Pluto had a moon, which he named Charon. The presence of this moon and its orbit provided the key to a precise calculation of Pluto's mass. The answer was a mere 0.002 Earth masses. This is approximately 3,500 times too small to create the gravitational perturbations that Lowell had attributed to his planet X. The fact that Pluto was found within 6 degrees of Lowell's predicted position had seemed like definitive confirmation, but it was ultimately a coincidence. Lowell's calculations were based on orbital residuals that later analysis revealed were mostly the result of measurement error. He had predicted a planet with 7 times the mass of Earth. What was found was a body smaller than Earth's own moon. The proximity of the discovery to the prediction was purely a matter of chance. The astronomical community understood this relatively early on, and by the 1940s, it was clear that Pluto was far too small to be Planet X, but the initial public excitement had already cemented Pluto's identity. Textbooks were updated to list 9 planets, and generations of schoolchildren memorized mnemonics to remember them. For 76 years, the question of whether a truly massive planet existed beyond Neptune was largely considered answered, buried under the assumption that Tombaugh had already found it. In August of 1989, the Voyager 2 spacecraft executed its flyby of Neptune. The probe had been launched 12 years earlier from Cape Canaveral and had already visited Jupiter, Saturn, and Uranus on a grand tour of the outer solar system, a journey made possible by a rare planetary alignment that happens only once every 175 years. Neptune was its final destination. On August 25th, Voyager 2 passed within 3,000 miles of Neptune's cloud tops. It measured the planet's magnetic field and photographed its largest moon, Triton. The images sent back were stunning, revealing geysers of nitrogen ice erupting from Triton's surface, creating thin plumes that stretched 5 miles high. The spacecraft also discovered 6 previously unknown moons, found faint rings where none had been confirmed before, and, most importantly, it produced an extremely precise measurement of Neptune's mass. That single measurement changed everything. Before Voyager 2, the mass of Neptune was known only through ground-based observations of its gravitational effects on other celestial bodies. Those observations had a margin of error, which, while small by astronomical standards at about 0.5%, was significant. 0.5% may sound trivial, and for most applications, it is. In this case, however, it was enough to create a phantom. The entire argument for Planet X, stretching all the way back to Percival Lowell, was built upon apparent irregularities in the orbit of Uranus. The planet was not moving exactly as predicted by Newton's laws, even after accounting for the known positions and masses of all other planets. The discrepancy between prediction and observation was small, but Lowell attributed that gap to the gravitational pull of an undiscovered planet orbiting beyond Neptune. Voyager 2's new, more accurate figure for Neptune's mass resolved the issue entirely. The old errors in calculation were just enough to account for the phantom perturbations in Uranus's orbit, meaning there was no need for a Planet X after all. The precise measurement of Neptune's mass by Voyager 2 caused the discrepancy in Uranus's orbit to vanish entirely. When scientists incorporated this corrected mass into their orbital calculations, the predicted path for Uranus aligned perfectly with its observed movements. There were no leftover perturbations and no sign of an anomalous gravitational tug. The need for a Planet X had been completely erased. The definitive analysis came from Miles Standish at NASA's Jet Propulsion Laboratory, who published his findings in 1993. He recalculated the orbital paths of the outer planets using the updated mass of Neptune derived from Voyager 2's flyby data. With this new information, every supposed anomaly in the motion of Uranus disappeared. The century-long search for Planet X, it turned out, had been chasing a phantom born from a measurement error. The fundamental issue was a matter of precision, or more accurately, the absence of it. While the visual observations of Neptune's position made by 19th century astronomers were good for their time, they were not quite good enough. An error of just 0.5% in the mass of a planet 17 times heavier than Earth translates into a significant gravitational miscalculation when projected across decades of orbital motion. The error compounded over time, growing larger the further into the past or future the predictions were extended. Lowell had built his entire prediction upon this very miscalculation. The fact that Tombaugh found Pluto in roughly the right area of the sky was a remarkable accident, a coincidence the astronomical community treated as confirmation for 7 decades. The Voyager 2 flyby brought that era to an end. After 1989, there was no longer any observational basis to believe a massive planet existed beyond Neptune. The perturbations were gone, and the math balanced. The idea of Planet X was effectively dead. It took time for textbooks to be updated, and public awareness lagged even further behind. For another 17 years, Pluto remained the ninth planet in the popular imagination. Within the professional community, however, the question was considered settled. The outer solar system was understood to contain 4 giant planets, a scattered field of icy debris, and Pluto, which was clearly something other than the world Lowell had predicted. No one was actively searching for a new planet anymore. The quest had consumed nearly a century of effort and yielded exactly one discovery: Pluto, which proved to be an answer to a flawed question. The case was closed, the file was archived, and for approximately 14 years, no one reopened it. That changed on November 14th, 2003, when Mike Brown, Chad Trujillo, and David Rabinowitz announced they had found an object they would later name Sedna. Brown was a professor of planetary astronomy at Caltech. Trujillo was a former student of his, working at the Gemini Observatory in Hawaii, and Rabinowitz was at Yale. Their discovery was made using the Samuel Oschin telescope at Palomar Observatory in Southern California, a 4-8-inch wide-field instrument that had been photographing the heavens since 1948. In terms of its physical properties, Sedna was fairly ordinary, another body of ice and rock in the outer solar system, measuring roughly 620 miles in diameter, about 1/3 the size of Pluto. The true puzzle, however, was its orbit. Sedna's closest approach to the Sun, its perihelion, occurs at a distance of 76 astronomical units. For comparison, Neptune orbits at 30 astronomical units, and Pluto's perihelion is at about 29. Sedna never comes anywhere near Neptune. Its farthest point from our star, its aphelion, is a staggering 937 astronomical units away. The object's orbital period is approximately 11,400 years. This meant that Sedna had last been at its closest point to the inner solar system around 9,400 BCE, long before the development of agriculture, writing, or the wheel. The orbit itself was highly elongated and tilted relative to the plane where the major planets travel. This combination of characteristics created a classification problem that had never been seen before. Sedna was too far from Neptune to have been scattered into its current path by a gravitational encounter. Objects that Neptune has ejected into distant orbits still pass through Neptune's neighborhood on each journey, but Sedna does not. It was also too close to have originated in the Oort cloud, the theoretical shell of icy objects thought to exist at 20,000 to 100,000 astronomical units. And its path was too eccentric for it to belong to the classical Kuiper belt, whose members travel in relatively circular paths between 30 and 50 astronomical units. Sedna resided in a kind of gravitational desert, a region of space where no known mechanism could have placed it. Brown called it the most scientifically important trans-Neptunian object found to date. Every previous discovery in the outer solar system could be explained by the gravitational influence of the 8 known planets. Sedna, however, could not. This immediately raised a profound question: how did Sedna get there? Several hypotheses began to circulate. A passing star in the solar system's early history might have pulled Sedna into its current orbit during a close flyby. Alternatively, the gravitational influence of other stars in the birth cluster where the Sun formed could have been responsible. Or perhaps something massive, something still out there, was maintaining Sedna's orbit through an ongoing interaction. Each idea presented problems. The passing star scenario required a very specific geometry. The birth cluster hypothesis was plausible but difficult to test, as the cluster dispersed billions of years ago. What limited any conclusion was the single object problem. One unusual orbit could be explained by many things, including a fluke encounter from the distant past. With only a single example, there was no way to distinguish between explanations. Brown and Trujillo knew they needed to find more objects like Sedna. They had to determine whether it was unique or a representative of a hidden population. If other bodies shared similar orbits, the resulting pattern might point to a cause, so they kept searching. In 2014, Chad Trujillo and Scott Shepard of the Carnegie Institution for Science announced they had found a second object with an orbit that resembled Sedna's. It was designated 2012 VP 113. Its perihelion was 80.5 astronomical units, even farther from the Sun than Sedna's closest approach. It, too, was located deep in that same gravitational desert, where nothing was expected to be. Two objects with such similar orbits was interesting. But what Trujillo and Shepard noticed next was more than just interesting. They plotted the orbital parameters of 2012 VP 113 alongside Sedna and 4 other extreme trans-Neptunian objects. The bodies in question were those with semi-major axes extending beyond 150 astronomical units and with perihelia located outside the orbit of Neptune. This collection comprised 6 objects in total. What was unusual was a peculiar property that all 6 of them shared. Their arguments of perihelion, which is a technical value that defines the orientation of an orbit's closest point to the Sun, were all grouped closely together near 0 degrees. In a solar system shaped only by known forces, these orientations ought to be distributed at random. One would expect them to be scattered evenly across a full 360 degrees. Instead, the arguments of perihelion for all 6 of these distant objects occupied the same very narrow sector. The researchers, Chad Trujillo and Scott Shepard, performed a calculation to determine the likelihood of such an alignment happening purely by chance. The result was a mere 0.007%, a probability of roughly 1 in 14,000. This striking figure, however, was predicated on the assumption that their sample was free from bias. It required that the 6 bodies were discovered by astronomical surveys capable of detecting them at any point in their orbits and with any possible orientation. If that assumption held true, then the observed clustering was in need of a powerful explanation. Trujillo and Shepard offered a potential one. They suggested that a massive, undiscovered planet orbiting in the far reaches of the solar system could be acting as a gravitational guide. The gravity from such a world would gently influence the orbits of smaller bodies over immense timescales. Throughout millions of years, it would gradually nudge their arguments of perihelion into a similar alignment. For this to work, the planet would have to be substantial, possessing a mass of at least several Earths. Its orbit would need to be hundreds of astronomical units from the Sun, and it would have to have existed there for billions of years, slowly shaping the orbital architecture of its distant neighborhood. Their paper detailing this hypothesis appeared in the journal Nature in 2014. The reaction from the broader scientific community was one of careful consideration. A sample size of 6 objects was acknowledged to be quite small. The surveys that had discovered them had only scanned limited areas of the sky. Consequently, the statistical weight of their finding was entirely dependent on whether this small sample accurately reflected the entire population of such objects. A number of other scientists noted that statistical analyses of small datasets can sometimes reveal patterns that disappear as more information becomes available. An apparent grouping among a few objects doesn't always signify a genuine clustering within the larger, unseen population. Others pointed out that the orbital alignment might simply be an artifact of where telescopes had been aimed, rather than a true reflection of where the objects were located. If surveys consistently favored certain regions of the sky, then any objects they found would naturally appear clustered in those directions, irrespective of their actual distribution. And yet, the pattern was undeniably there. 6 bodies, scattered across billions of miles of space, found by separate teams with different telescopes over many years, all shared an orbital feature that statistics suggested was almost impossible to achieve by accident. These objects had been located over a period of more than a decade by various observatories in different hemispheres, using a range of instruments with varying sensitivities, yet they all pointed in the same direction. Trujillo and Shepard were very deliberate with their wording. They laid out the data and put forward the planet hypothesis as just one of several possible interpretations. They advocated for further observations and a more thorough analysis of potential survey biases. At Caltech, 2 other researchers were already following these developments with great interest. Mike Brown's social media handle was a direct reference to Pluto, a moniker he felt he had earned. In 2005, Brown's team had discovered Eris, an object residing in the scattered disk far beyond Neptune. Eris was found to be about the same size as Pluto, and possibly even more massive. Its existence compelled the International Astronomical Union to confront a question it had long deferred. If Pluto was a planet, then Eris must be a planet as well. And what about the other large bodies Brown's team was finding, such as Makemake, discovered in 2005, or Haumea, identified that same year? The Kuiper Belt was revealing itself to be populated with numerous Pluto-sized worlds. The choice was either to accept that the solar system had a dozen or more planets, or to reconsider Pluto's classification. In August of 2006, the International Astronomical Union cast its vote. A new category, dwarf planet, was established, and Pluto was placed within it, along with Eris and Ceres. Pluto was officially no longer the ninth planet. Brown had been the catalyst for this demotion. He even wrote a book about the experience, giving it the title, How I Killed Pluto and Why It Had It Coming. He was not apologetic for his role, arguing that Pluto had never really met any scientifically robust criteria for being a planet. In his view, it was simply one of many thousands of icy bodies that orbited in the Kuiper Belt. To call it a planet was an act of sentimentality, a historical accident that was scientifically confusing. The public did not universally share this perspective. Brown was sent hate mail, and school children penned angry letters to him. He embraced the controversy, and the Pluto handle remained. Konstantin Batygin was a scientist of a different sort. A theorist who was born in Moscow in 1986. He was raised for a time in Japan and later educated at the University of California, Santa Cruz. He first came to Caltech as a postdoctoral researcher and subsequently joined the faculty. His expertise was in orbital dynamics, the complex mathematics describing how celestial bodies move under the influence of gravity over cosmic timescales. He specialized in creating models that simulated how planetary systems change over millions and even billions of years. In 2016, Brown and Batygin co-authored a paper for the Astronomical Journal. Its title was direct, Evidence for a Distant Giant Planet in the Solar System. Their work proposed the existence of a planet with a mass between 5 and 10 times that of Earth. This world would be orbiting our star at an immense distance, somewhere between 400 and 800 astronomical units. Its orbital period would be extraordinary, lasting from 10,000 to 20,000 years. The paper was exceptionally rigorous. It reached far beyond the clustering of 6 objects that Trujillo and Shepard had first identified. Brown and Batygin demonstrated how their single hypothetical planet could account for several distinct and previously unexplained features of the outer solar system all at once. This included the alignment of orbital orientations, the presence of objects with orbits tilted perpendicular to the plane of the major planets, and even the slight tilt of the entire planetary plane relative to the Sun's equator. A single planet offered multiple solutions. The man who had effectively removed the ninth planet was now proposing its true replacement. This would be a real ninth planet, massive enough to gravitationally dominate the far outer solar system, yet so distant and faint that it had eluded every survey to date. Brown had spent the prior decade making the case that Pluto was not a genuine planet. Now, he was claiming to have found evidence for something that truly was. The paper quickly amassed over 1,500 citations in just its first few years. It ignited one of the most significant discussions in planetary science in decades. Observatories across the globe began dedicating telescope time to scan the predicted patch of sky. The hunt for what came to be called Planet 9 was officially underway. The power of the Batygin and Brown model was rooted in its predictive capacity. A strong scientific hypothesis does more than just explain the data we already have. It also makes predictions about what else we should be able to find. It puts itself at risk of being disproven in specific, testable ways if it is incorrect. Planet 9, as the media had swiftly christened it, made just such specific predictions. The first of the model's predictions centered on objects in perpendicular orbits. The simulation indicated that a very massive planet, orbiting at several hundred astronomical units, would over time gradually torque certain trans-Neptunian objects. Their paths would become tilted by roughly 90 degrees in relation to the plane shared by the 8 known planets. If Planet 9 were real, then these perpendicular objects should also be real, and as it turned out, they were. 5 such trans-Neptunian objects, traveling along these highly inclined orbits, had in fact been discovered prior to the 2016 paper's publication. At the time, no one had a compelling explanation for their existence. The Planet 9 model, however, offered a reason without being specifically configured to do so. The existence of these perpendicular orbits simply emerged from the mathematics as a natural consequence. Batygin and Brown had not set out to engineer this particular outcome in their model. They were simulating the long-term orbital evolution of trans-Neptunian objects under the influence of a distant, massive body. The population of perpendicular objects appeared on its own. It was an emergent property of the gravitational dynamics at play. When the researchers consulted astronomical catalogues, they found the objects their model predicted were already there. A second prediction from the model was more subtle. It suggested that the gravitational pull of Planet 9 would cause the orbital plane of the 8 known planets to tilt. This tilt would be in relation to the spin axis of our host star. The expected angle of this tilt was approximately 6 degrees. For decades, astronomers had been aware that the planet's orbital plane is indeed tilted by about 6 degrees relative to the Sun's equator. This observed tilt lacked any widely accepted explanation. The Sun formed from a spinning disk of gas and dust. The planets coalesced from that very same disk. Logically, they should all share the same orbital plane, but they do not. Planet 9 provided a potential reason for this discrepancy. A distant, massive object on an inclined orbit would cause the entire inner planetary system to slowly precess. Over the course of billions of years, this effect would tilt the system's plane away from the star's spin axis. The model produced a value of exactly 6 degrees. This alignment was not forced. Bettigan and Brown did not manipulate their planet's parameters to arrive at this specific number. It arose from the same model that accounted for the orbital clustering. This type of result carries significant weight in physics. It is rare for a single hypothesis to independently resolve several unrelated puzzles. Each mystery it clarifies, without being specifically tailored to do so, bolsters confidence that the hypothesis may reflect something true about the universe. The orbital clustering of extreme trans-Neptunian objects was one puzzle. The existence of perpendicular orbits was another. The 6-degree obliquity of our star's spin axis was a third. The detachment of bodies like Sedna from the inner solar system was a fourth. Planet 9 seemed to connect these 4 separate mysteries. The model also generated predictions that remained to be tested. It outlined a specific region of the sky where the planet ought to be found. It also constrained the planet's expected brightness across various wavelengths of light. Furthermore, it described the orbital characteristics of other trans-Neptunian objects that should be discovered by future surveys looking in the correct locations. These untested predictions supplied the hypothesis with something that earlier ideas had been missing: genuine, high-stakes falsifiability. If an instrument like the Vera Rubin Observatory were to complete its 10-year survey and find no planet within the predicted mass and orbital range, the hypothesis would face serious difficulty. Bettigan and Brown accepted this possibility. In fact, they welcomed it. A hypothesis that cannot be invalidated by data does not belong to the realm of science. Planet 9 could be invalidated by data. That is precisely what made it a concept worth investigating. Samantha Lawler, however, did not believe the evidence was sound. Lawler was an astronomer at the University of Victoria in British Columbia. Her work involved the Outer Solar System Origins Survey, known by the acronym OSOS. This survey utilized the Canada-France-Hawaii telescope, or Mauna Kea, to systematically chart trans-Neptunian objects. From its very inception, it was designed to meticulously account for observational bias. This term, observational bias, formed the very core of Lawler's critique of the Planet 9 hypothesis. Telescopes are not all-seeing. They can only observe what is possible given their specific location, their field of view, the time of year, the sensitivity limits of their instruments, and the patches of sky their operators decide to study. Consequently, the objects discovered in any survey reflect both the true population and the survey's inherent blind spots. An object located in a part of the sky where a telescope never pointed might as well not exist for that survey. In 2017, Lawler and her colleagues published their analysis. They investigated whether the orbital clustering identified by Trujillo, Shepard, Bettigan, and Brown could simply be an artifact of where astronomers had aimed their telescopes. The conclusion, according to the OSOS team, was yes. The survey group constructed detailed simulations. They modeled what a uniform, unclustered population of trans-Neptunian objects would look like if it were observed using the actual telescopes and survey strategies that had been employed. These simulations produced what appeared to be clustering. Objects seemed to group together in particular orbital orientations. This occurred even though the underlying population in the model was evenly distributed. The The bunching effect was like a shadow cast by the survey's geometry onto the data. Lawler's team argued that the 0.007% probability calculated by Trujillo and Shepard was therefore without meaning. That figure was based on the assumption of unbiased detection. If the detections were biased, which they almost certainly were to some extent, then the probability calculation was founded on a false premise. The impressive-looking statistic was merely an artifact of incomplete accounting. The OSOS project had characterized its own biases exhaustively. Every single pointing and exposure time was recorded and made public with the data, along with every detection limit. When the team analyzed only the objects discovered by OSOS itself and applied their own rigorous bias corrections, the clustering signal vanished. The objects they found were consistent with a uniform distribution. No shepherding planet was needed to explain them. This argument struck at the heart of the matter. It did not directly disprove the existence of Planet 9. Instead, it attacked the statistical foundation upon which the entire hypothesis was built. If the clustering was just an artifact, the primary line of evidence would simply evaporate. Batygin and Brown offered a rebuttal. They argued that the OSOS survey had discovered too few extreme trans-Neptunian objects to draw any firm conclusions about clustering. The OSOS sample size contained only a handful of objects in the relevant orbital range. Such small samples are statistically compatible with almost any underlying distribution. They also highlighted that the OSOS analysis focused narrowly on the clustering evidence. It seemed to ignore the perpendicular orbits and the 6-degree obliquity prediction. These features were independent of any survey bias. They existed as facts, regardless of where telescopes had been looking. The debate that followed became one of the more contentious in modern planetary science. Both sides proceeded to publish detailed counterarguments and rebuttals. At conferences, competing presentations became a common feature, and graduate students learned to discern which intellectual camp their advisors belonged to before settling on a thesis topic. The astronomical community had fractured, and this division was not merely academic. Access to major telescopes is a strictly limited resource, meaning every hour dedicated to the search for Planet 9 was an hour that could not be used for other scientific inquiries. If the planet was a reality, the extensive search was a worthy endeavor. If, however, it was just a statistical illusion, the community was spending its precious observation time in pursuit of a phantom. The consequences of this debate reached far beyond the scope of any individual career or scientific paper. Then, on October 1st, 2018, Scott Shepard and his collaborators announced they had found a new object, designated 2015 TG 387. They nicknamed it the Goblin, a name inspired by the TG in its official label and the timing of the announcement near Halloween. The name proved popular. The Goblin itself was small, measuring about 200 miles in diameter, just another piece of ice and rock moving through the distant outer solar system. In terms of its size, there was nothing particularly special about it, but its orbit was another matter entirely. Its perihelion was 65 astronomical units from the Sun, far beyond the primary gravitational grasp of Neptune. The semi-major axis of its orbit was a vast 1,170 astronomical units, and its orbital period was estimated at 40,000 years. To put that in perspective, the last time the Goblin was at its closest approach to our star, modern humans were painting on the walls of caves in southern Europe and crossing ancient land bridges into new continents. Shepard's team conducted a series of dynamical simulations to test the stability of the Goblin's orbit under two conditions, one with Planet 9 and one without. The results were unambiguous. In a solar system without Planet 9, the Goblin's orbit was unstable over billions of years. Gravitational disturbances from the known giant planets would eventually either eject it from the solar system or completely reshape its path. Yet when Planet 9 was included in the simulation, using the mass and orbital parameters from the Batygin and Brown model, the orbit unraveled. The Goblin's path remained stable for the entire 4 billion, 5 billion year history of the solar system. The hypothetical planet acted as a gravitational shepherd, providing subtle nudges to the Goblin at regular intervals. This influence maintained the object's elongated orbit through a process known as mean motion resonance. This cosmic timing ensures that for every single orbit the Goblin completes, Planet 9 completes a specific whole number ratio of its own orbits, preventing the two bodies from ever getting close enough for a disruptive gravitational encounter. The Goblin also aligned perfectly with the clustering pattern. Its argument of perihelion was consistent with the other extreme trans-Neptunian objects, and it was discovered in a region of the sky that the OSS-OS bias analysis had difficulty accounting for. The analysis from Lawler's team had specifically detailed the biases of particular surveys. The Goblin, however, was found by a completely different survey that used another telescope, had different sky coverage, and observed during different seasons. Each new object identified by an independent survey made the observational bias explanation more difficult to maintain. That argument depended on the idea that every survey, run by different teams with different instruments aimed at different parts of the sky at different times of the year, all happened to share the exact same systematic flaw. While possible in theory, this position became increasingly hard to defend as new data points emerged. Shepard made a point to highlight this in the discovery paper. The Goblin was now the third object, following Sedna and 2012 VP-113, with a perihelion far from Neptune and an orbit that was consistent with being shepherded by Planet 9. These were three objects found by three separate surveys using three different telescopes. In response, Brown and Batygin revised their orbital model, incorporating the Goblin and other new findings. This updated model further refined the predicted mass and orbit of Planet 9. Every new extreme trans-Neptunian object served as an additional constraint, shrinking the area of parameter space where the planet could possibly be hiding. The discovery of the Goblin did not prove the existence of Planet 9. Definitive proof would require direct detection, a photograph, a spectrum, a confirmed point of light at the predicted location, moving at the predicted speed. But the Goblin added significant weight to the hypothesis. It was another piece of evidence that behaved precisely as the model anticipated. Another object whose orbit was more coherent in a solar system with 9 planets than one with only 8. Back in 1983, NASA had launched a satellite carrying an infrared telescope into a polar orbit. The mission was called IRAS, the Infrared Astronomical Satellite. It was the very first instrument to map the entire sky in infrared light, and it operated for only 10 months before its liquid helium coolant evaporated, causing its detectors to warm up and cease functioning. In that short operational window, IRAS managed to catalogue approximately 350,000 distinct infrared sources, including stars, galaxies, dust clouds, asteroids, and faint, unidentified smudges. The data was archived and released to the public. For decades, scientists sifted through this catalogue, mining it for brown dwarfs, distant galaxies, and young stellar objects, but no one was looking for a planet. Then, 42 years later, a researcher named Terry Longfan pursued an idea that was almost deceptive in its simplicity. He took the IRAS catalogue and cross-referenced it with data from Akari, a Japanese infrared satellite that conducted its own all-sky survey in 2006. This gave him 2 complete datasets from 2 different missions, separated by a 2-3-year interval. If an object in the IRAS data had moved between 1983 and 2006, it would show up at slightly different coordinates in the 2 catalogues. A star would not have moved, nor would a galaxy. A planet, however, would. Longfan began with a list of roughly 2 million sources. He then applied a series of filters for brightness, color temperature, and positional uncertainty. The list began to shrink, from 2 million to a few thousand, then from a few thousand to a few hundred, and finally from a few hundred down to just 13. These were 13 objects that appeared in both catalogues at positions that were consistent with slow, steady motion across the sky. 13 candidates that could potentially be the same object observed 23 years apart. Among those 13, one in particular stood out. It had shifted its position by approximately 47 arc minutes between the 2 surveys. This is a very small angle, less than the apparent diameter of the full moon. But for an object in the far outer solar system, this is exactly the kind of movement one would expect. Slow, deliberate, and consistent with something orbiting the sun at an immense distance. The implications of this were profound. If Longfan's candidate is confirmed to be real, it means that Planet 9 was already photographed back in 1983. It suggests the planet has been sitting in a public database for the entire time. After 4 decades of searching, of modeling, of debating orbital parameters and statistical significance, the evidence may have been archived on magnetic tape in a government data center since the Reagan administration. There are, of course, important caveats. The IRS satellite had low spatial resolution by today's standards. Its pixels were large, which means the positional uncertainties are significant, sometimes spanning several arc minutes in a single measurement. One distinct possibility was that the candidate was not a single object, but 2 completely separate sources that simply appeared near one another in the sky when observed across a 2-3 year baseline. Infrared catalogs are notoriously crowded environments where faint sources can easily blend together, and where instrumental artifacts often masquerade as genuine celestial bodies. A lone coincidence, therefore, is not enough to confirm a discovery. True validation demands follow-up observations aimed at the object's predicted current position. If the body is real and has maintained its trajectory, it should now reside at a precise set of coordinates, which can be calculated from the 2 previous measurements. The next step is to point a modern infrared telescope at that exact spot in space. If something is detected there, the cold case is effectively solved. While that verification work is still underway, the mere possibility has fundamentally altered the discussion. It introduced the intriguing idea that the hunt for Planet 9 has been a cold case all this time. The photograph was already taken. The data had been gathered, archived, indexed, and then offered freely to anyone with access to the internet. All that was needed was for someone to open the file and see what was there. For 41 years, no one did. The world that Konstantin Batygin and Mike Brown envisioned in 2016 was a super-Earth, a planet somewhere between 5 and 10 times the mass of our own. It could have been rocky, or perhaps it was shrouded in a thin envelope of hydrogen and helium. It was thought to be dense enough to shape the paths of distant, icy objects, yet small enough to have remained hidden throughout the entire history of telescopic astronomy. The mass estimate of 4.4 Earth masses, published in 2025, seemed to support this view of a middleweight planet, larger than Earth but smaller than Neptune, lurking in the darkness. However, Terry Longfan's IRIS candidate complicated this entire picture. The central issue was its brightness. If the source found in the IRIS data is truly a planet at the forecast distance, its infrared emissions suggest something much larger than a super-Earth. In fact, it would have to be significantly larger. The thermal signature aligns more closely with a body in the mass range of Uranus or Neptune, a gas giant, or at the very least an ice giant with a substantial atmosphere of hydrogen, helium, methane, and ammonia. This discrepancy was important for a number of reasons. A super-Earth located at 500 astronomical units could conceivably have formed in the inner solar system before being flung outward by gravitational encounters with Jupiter or Saturn during the chaotic early era of planetary migration. The physics behind this scenario is sound, the timescales are plausible, and models can reliably reproduce such an event. An ice giant, on the other hand, is far more difficult to account for. Uranus and Neptune themselves barely had sufficient time to coalesce where they are now, at roughly 19 and 30 astronomical units from the Sunday. The outer solar system was simply too sparse, too cold, and its raw materials too thinly distributed for giant planet cores to form quickly. Moving that formation challenge out to 500 astronomical units magnifies the problem by orders of magnitude. Standard core accretion theory offers no known mechanism that could produce a Neptune-mass planet at such an extreme distance. The alternative explanation is that it formed closer to the Sun and was subsequently scattered outward, the same story proposed for the super-Earth version. But scattering a more massive planet would necessitate a much more violent interaction. The energy requirements change, the probability of such an event decreases, and the resulting orbit is harder to align with the relatively stable, near-circular path that the clustering of trans-Neptunian objects appears to require. Then there is the matter of its detection. Astronomers have been scouring the skies for Planet 9 using some of the most powerful survey instruments ever constructed. If the object is a super-Earth, its faintness is understandable. A rocky body 5 times Earth's mass at 500 astronomical units would reflect a negligible amount of light from our star and emit very little of its own infrared radiation. It would be exceptionally dim, bordering on invisible. A Neptune mass body, however, would be brighter, with a larger surface area and more atmospheric gas to reflect starlight, as well as more internal heat to radiate. The fact that an object of this size has eluded discovery for so long raises some difficult questions. Perhaps the orbital predictions are slightly inaccurate, and the search has been focused on the wrong patch of sky. Or maybe the planet is situated within a dense region of the Milky Way's galactic plane, where it is lost among a crowd of background stars. Another possibility is that the surveys have not yet looked deep enough in the correct wavelengths. Each of these potential answers has its own set of implications. The search is no longer just about discovering a planet. It has become a quest to understand what kind of planet could possibly exist where no planet should be. In 2019, a paper from two physicists at Durham University proposed something truly unusual. Jacob Schultz and James Unwin suggested that the gravitational anomalies observed in the outer solar system might not be caused by a planet at all, but by a primordial black hole. This idea requires some background. Black holes exist in various sizes. Those that form from the collapse of massive stars are typically several times the mass of our Sunday. The supermassive black holes found at the centers of galaxies can weigh millions or even billions of times more. Yet, theoretical physics permits a third category. In the first moments after the Big Bang, when the universe was incredibly dense and hot, it is thought that random fluctuations in the distribution of matter could have compressed small regions beyond their Schwarzschild radius. These pockets would have instantly collapsed into black holes, not stellar mass, not supermassive, but tiny and primordial. A primordial black hole with the mass of 5 Earths would measure roughly 4 inches in diameter, about the size of a tennis ball. It would warp space-time with the exact same gravitational influence as a rocky or icy planet of identical mass. Every trans-Neptunian object that Planet 9 is thought to be shepherding would behave in precisely the same manner in the presence of this black hole. The orbits would still cluster. The trajectory of Sedna would still make sense. The Goblin would still fit the model. From a purely gravitational standpoint, the two explanations are indistinguishable. The crucial difference, however, is that a primordial black hole would be invisible. It emits no light and reflects no light. It has no atmosphere to scatter photons and no surface to radiate heat. Every telescope ever pointed toward the outer solar system would have seen nothing. Infrared surveys would have found nothing. Optical surveys would have found nothing. The object would be gravitationally present but electromagnetically absent. Schultz and Unwin acknowledged that this made their hypothesis extremely difficult to test. They offered it partly as a thought experiment, a way to demonstrate that the gravitational evidence for Planet 9 does not exclusively point to a planet. It points to the existence of mass, while the true nature of that mass remains an open question. A year later, researchers Amir Siraj and Avi Loeb at Harvard presented a possible method of observation. Their argument suggested that a primordial black hole traversing the outer solar system would occasionally cross paths with smaller bodies like comets and asteroids. These are chunks of ice on long, isolated trajectories. When one of these celestial objects happened to wander sufficiently close, it would be torn asunder by the black hole's tidal forces. The resulting debris would then spiral toward the event horizon, heating up to extreme temperatures along the way. For a fleeting moment, this interaction would generate a burst of radiation, a flash that could be seen in the right wavelength. It would be a momentary event, easily missed, but a wide-field survey telescope constantly watching the sky might just catch one. The rate of detection would likely be low, possibly just a handful of these flares each year. This frequency would be contingent on the density of small bodies in that region of space. Each flare was predicted to last for hours, or perhaps even days. While the signal itself would be faint, it would be present. Its location would allow astronomers to trace the path of the invisible object that created it. To date, no one has observed such a flare. The technology for a systematic search is only just becoming available. Consequently, the idea remains precisely what it is, a hypothesis. But it persists in scientific literature, serving as a reminder that the outer solar system could harbor objects that do not conform to the simple category of a planet. In 2023, a different team of scientists proposed that the entire Planet 9 hypothesis might not be needed. Their reasoning did not depend on a black hole, a hidden planet, or any other unseen object. Instead, it focused on the nature of gravity itself. This framework is known as modified Newtonian dynamics, or MOND. It was first put forth in 1983 by the Israeli physicist Mordechai Milgrom as an alternative explanation for dark matter. Milgrom observed that the rotation curves of galaxies presented a puzzle. Stars orbit their galactic centers at speeds that appear too high to be explained by the visible mass alone. He found these speeds could be accounted for by adjusting Newton's law of gravitation at extremely low accelerations. Below a particular threshold, gravity would act in a slightly different manner than what Newton had predicted. It would be stronger and more persistent, enough to bind galaxies together without needing to invoke any invisible matter. MOND has existed for 4 decades on the fringes of mainstream physics. It describes galaxies with surprising accuracy, often better than it should. However, it does not work for clusters of galaxies. It also lacks a fully developed relativistic formulation, although several attempts have been made. The majority of physicists consider it an interesting and sometimes useful concept, but one that is likely incorrect. Dark matter continues to be the prevailing paradigm. Nevertheless, the 2023 paper applied MOND to the outer solar system. At distances of several hundred astronomical units from the Sun, gravitational acceleration diminishes to levels near Milgrom's threshold. The authors demonstrated that within this regime, the galactic tidal field, the very gentle gravitational influence of the Milky Way itself, could create an alignment effect among the orbits of distant trans-Neptunian objects. The very clustering that Batygin and Brown had ascribed to a hidden planet could arise as a natural consequence of the interplay between a modified law of gravity and the galaxy's own gravitational pull. This explanation required no planet, no black hole, and no extra mass of any kind. It simply proposed a different equation for how gravity behaves when it becomes exceptionally weak. The significance of this argument is hard to overstate. If MOND is the correct explanation for the orbital clustering in the outer solar system, it would mean that Isaac Newton's law of universal gravitation is incomplete. That law works flawlessly for falling apples, for cannonballs, and for the orbit of the Moon. It functions perfectly for Mercury and Mars, and for the path of every spacecraft ever sent into space. But at the most distant reaches of the Sun's gravitational influence, where acceleration falls to less than a billionth of what one feels on Earth's surface, the law would break down. Such a discovery would be far more significant than finding any new planet. It would signify that the fundamental description of gravity used in physics for more than 3 centuries requires revision. It would also strengthen the case for MOND as a legitimate alternative to dark matter. It would necessitate rewriting textbooks. The paper was greeted with considerable skepticism. Those who advocated for MOND saw it as a form of vindication. Supporters of Planet 9 viewed it as a mathematical exercise that was disconnected from the complete body of evidence. Critics noted that MOND's predictions for the outer solar system are sensitive to assumptions about the galactic tidal field, which remains poorly understood. Furthermore, the ongoing debate about the clustering itself, whether it is a real phenomenon or just a result of observational bias, applies just as much to the MOND explanation. If the clustering is not real, then MOND has no more need to explain it than Planet 9 does. The central question had shifted. It was no longer just about whether a planet exists beyond Neptune. It was now about whether we truly understand the fundamental force that holds our solar system together. Its formal name is 2017 OF201. However, most people who follow the Planet 9 debate know it by its nickname, Ammonite. This object measures roughly 430 miles in diameter. It is a mid-sized trans-Neptunian body, similar in scale to some of the larger objects found in the Kuiper Belt. Its orbital period is about 25,000 years. It follows a long, highly elliptical path that takes it from a perihelion relatively near Neptune's orbit to an aphelion so far away that the Sun would look like little more than a brilliant star. Ammonite would otherwise be unremarkable were it not for one specific detail. Its orbit is tilted at an angle of roughly 90 degrees away from the predicted orbital plane of Planet 9. This detail is crucial because the entire Planet 9 hypothesis is built upon the concept of a massive, unseen body, gravitationally herding distant objects into aligned orbits. The clustering of these trans-Neptunian objects, the shared orientation of their orbital planes, and the common direction of their closest approach to the Sun are the key pieces of evidence. Planet 9 is thought to maintain this alignment by gently nudging any objects that stray too far back into the group. This is much like how a sheepdog keeps a flock of sheep moving together in a single direction. Ammonite, however, seems to have wandered off in the wrong direction entirely, and its discovery was unexpected. When its orbit was calculated and made public, opponents of the Planet 9 hypothesis immediately pointed to it as counter-evidence. Here was an object from the very population that Planet 9 was supposed to be controlling, yet its orbit directly contradicted the predicted alignment. If this gravitational shepherd truly exists, how did this particular sheep end up 90 degrees off course? Proponents of the hypothesis offered several counter-arguments in response. They explained that the gravitational influence of Planet 9 is complex. It does not simply force every object into the exact same orbital configuration. Computer simulations indicate that a certain percentage of trans-Neptunian objects should be scattered into perpendicular or even backward orbits through a process known as the Kozai mechanism. A gravitational process known as the Kozai mechanism was put forward, a slow exchange that transforms an object's orbital tilt into a more elliptical shape over vast stretches of time. Within this particular framework, the outlier known as 2015 BP 519 was not seen as evidence against Planet 9, but rather as one of its predicted byproducts. There is, however, a significant difference in the weight given to predictions made before an event compared to those offered after the fact. The Kozai mechanism was only applied to explain this specific object once it had already been discovered. Prior to its detection, the prevailing narrative had focused almost exclusively on the clustering and alignment of distant orbits. The possibility of a major outlier was not a prominent part of the discussion. This reveals a recurring pattern throughout the story of Planet 9, where the central hypothesis demonstrates a remarkable flexibility. When newly found objects conform to the predicted alignment, they are held up as evidence that supports the theory. But when other new objects deviate from that pattern, the model is adjusted to accommodate them through secondary effects. While flexibility is not necessarily a flaw in a scientific model, as real gravitational systems are incredibly complex, a planet's influence would certainly create a diverse range of orbital outcomes. The danger, however, is that a model capable of explaining any possible observation risks, explaining nothing at all in a meaningful way. The discovery of 2015 BP 519 did not invalidate the Planet 9 hypothesis, as a single object rarely has the power to do so. What it did was introduce a specific and uncomfortable form of doubt. It demonstrated that the outer solar system contains bodies that do not conform to the predictions of the simplest version of the model. This, in turn, provided critics of the hypothesis with their first piece of concrete orbital evidence, suggesting the apparent clustering might be less organized than initially believed. The sheep had wandered from the path. The question became whether the shepherd was an illusion, or if the flock had always been wilder than anyone had assumed. By the year 2025, the debate over Planet 9 had settled into a deep divide, a statistical impasse. Both camps were armed with numbers, and both expressed great confidence, yet their figures were in stark disagreement. Konstantin Batygin and Mike Brown asserted that the probability of the observed orbital clustering of trans-Neptunian objects happening by mere chance was exceptionally low, at roughly 0.007%, or about 1 in 14,000. They had revisited and updated their analysis on multiple occasions since 2016, refining their sample of objects, adjusting for known biases, and incorporating new discoveries. Through it all, the number remained remarkably consistent. The clustering, they argued, was a real phenomenon that demanded a physical explanation, and the most straightforward explanation was a planet. On the opposing side was the Outer Solar System Origins Survey, or OSSOS, a Canadian-led initiative that utilized the Canada-France-Hawaii telescope for a meticulously planned search for trans-Neptunian objects. The OSOS team did something that most previous surveys had not. They painstakingly documented their own observational biases. They recorded precisely where they looked, when they looked, the depth of their observations, and what they could and could not have possibly detected. Their conclusion was a powerful counterargument. They proposed that when one properly accounts for the fact that most surveys tend to observe specific regions of the sky at particular times of the year, the apparent clustering of these distant orbits significantly diminishes. The objects seem to be grouped together, they contended, simply because we discovered them in the places we were already looking. If you aim a telescope at one small patch of the sky for 1,000 hours, but at another for only 10, you will inevitably find more objects in the first location. This does not imply that the objects themselves are clustered there. It means your survey created the pattern. This profound disagreement was not a matter of fraud or scientific incompetence. Both groups had their work published in peer-reviewed journals, and both employed valid statistical techniques. The crucial difference was rooted in how each team chose to address the complex issue of observational bias. This is a question for which there is no universally accepted answer, especially when the sample size is as small as it was. At the time, fewer than 25 extreme trans-Neptunian objects were known. A data set of just 25 points in almost any other scientific field would be considered far too small to justify more than a preliminary presentation at a conference, let alone a decade of intense international debate. But the outer solar system is notoriously sparse with its data. Pinning down the precise orbit of each new object requires years of patient observation. The rate of discovery is glacial, amounting to just 1 or 2 new objects in a productive year. This scarcity created a peculiar dynamic in the field. Every single new discovery possessed the potential to dramatically shift the statistical balance of the argument. A newly found object that fit the clustering pattern would strengthen the case made by Batygin and Brown. Conversely, a new object that did not fit would weaken it. The entire field seemed to exist in a state of permanent instability, where the very next data point could swing the needle of evidence in either direction. Some astronomers began to draw parallels between this situation and a replication crisis. The initial result, the clustering, had been published with a high degree of confidence, but subsequent independent efforts to confirm it yielded conflicting outcomes. The signal appeared to be present if one analyzed the data using a particular method, but it would vanish if the data was analyzed in a different way. Crucially, no one could agree on which method was the correct one to use. This war of statistics revealed something unsettling about the scientific process itself. It showed that when data is extremely limited and the stakes are high, it is possible for reasonable people using reasonable methods to arrive at diametrically opposed conclusions. The argument was no longer just about the contents of the outer solar system. It had evolved into a deeper conversation about the fundamental limits of statistical inference at the frontiers of observation. A decade prior, in 2006, a Brazilian astronomer named Rodney Gomes had published a quiet paper in the journal Times Icarus Asterisk. Gomes, who worked at the National Observatory in Rio de Janeiro, specialized in orbital dynamics, the intricate mathematics describing how gravitational forces shape the paths of bodies in the solar system over millions and billions of years. Gomes had been studying the scattered disk, a population of icy objects beyond Neptune that travel on highly elliptical orbits. These objects were understood to have been thrown outward during the early history of the solar system, a chaotic period when the giant planets were migrating and settling into their modern-day positions. While the known planets could explain the orbits of most scattered disk objects, a small handful of them, those on the most extreme trajectories, defied this explanation. Their perihelia, or closest approaches to the Sun, were too high, their orbits too detached from Neptune's gravitational influence. Something else had to have lifted them away. Gomes proposed that a distant, massive planet could be responsible for these anomalies. His calculations estimated a world roughly the mass of Neptune, orbiting the Sun at a distance of approximately 200 astronomical units. Such a planet, he theorized, would gravitationally interact with objects in the scattered disk over many millions of years. Over this immense timescale, it would gradually raise their perihelia, effectively detaching their orbits from the influence of the known giant planets. His paper received only modest attention at the time, a few citations, and a brief mention in academic reviews before it was largely forgotten. 10 years later, Batygin and Brown published their Planet 9 hypothesis to international acclaim, built upon a core idea that was almost identical. Gomes had envisioned a massive planet in the distant solar system. Its gravitational pull could shape the orbits of extreme trans-Neptunian objects through long-term interaction. The details of Batygin and Brown's work, however, were different. They concentrated on the phenomenon of orbital clustering instead of perihelion detachment. the planet they predicted was lighter and positioned farther out in space. While their mathematical framework was more elaborate, the conceptual skeleton of the idea was the same. Gomes, however, did not receive significant credit. He was occasionally cited in the scientific literature as a precursor, becoming a footnote in the history of the search. The narrative that took hold, both in the popular press and throughout much of the scientific community, was that Batygin and Brown had discovered the possibility of a ninth planet. The earlier work was acknowledged, but it was not given a central role. This pattern is older than any living astronomer. Percival Lowell predicted a trans-Neptunian planet in the early 1900s. He used calculations that were later shown to be based on errors in Neptune's mass. He was right about the existence of something out there, but he was wrong about every single detail. Clyde Tombaugh found Pluto in 1930 using Lowell's predictions, but Pluto turned out to be far too small to be the object Lowell had foreseen. It was the right answer, found for the wrong reasons. It was the wrong object, discovered in the right place. Gomes may have been the inverse case. He had the right reasons and the right general framework, but he was a decade too early. The field was not yet ready. The available data was not dense enough. The statistical tools were not mature enough to make the case with the kind of force that commands attention. Science rewards not just the first person to see something, but the first person to make others see it. Gomes saw it. Batygin and Brown made the world look. History will eventually sort out who deserves what credit. It usually does, but eventually can take a very long time. What is most interesting about Terry Longfan's study is not what he found. It is what his finding reveals about the machinery of scientific progress and the places where that machinery can stall. The IRAS data has been publicly available since 1984. It is archived. It is downloadable. It has been hosted on NASA servers for over 4 decades. Any astronomer with a computer and a basic understanding of infrared catalog analysis could have done what Fan did. The technique he employed is straightforward. It involves cross-referencing 2 all-sky infrared surveys taken at different epochs to look for objects that change position. This is the kind of analysis that gets assigned as a graduate student exercise. This is not because it is trivial, but because the underlying method is well understood and the tools are accessible. Yet nobody tried. For 41 years, the data sat in the archive. Hundreds of papers were written using IRAS observations. Thousands of astronomers accessed the catalogue. The idea that a faint, slowly moving object might be hiding in the source list was not conceptually difficult. It was, in fact, exactly the kind of thing that IRAS was uniquely positioned to detect. An infrared survey does not care whether an object reflects visible light. It sees thermal emission. A cold planet in the outer solar system would glow faintly in the infrared, even if it was utterly invisible to optical telescopes. So why did nobody look? The answer has less to do with technology or methodology and more to do with assumption. In 1989, Voyager 2 flew past Neptune. This allowed astronomers to precisely measure the planet's mass. The updated mass resolved the orbital discrepancies that had motivated the search for Planet X since the late 19th century. There was no missing mass. There was no need for an additional planet. The case was closed, and when a case is closed, people stop investigating. An assumption of emptiness settled over the outer solar system like sediment. Textbooks were updated. Funding priorities shifted. The Kuiper Belt was discovered and explored. But the search for a large, distant planet was considered a historical curiosity. It was something that Percival Lowell obsessed over, something that serious modern astronomers had moved beyond. This assumption was never stated as a formal conclusion. Nobody published a paper titled "There is definitely nothing else out there." It was more subtle than that. It was a collective turning of attention. It was a shared sense that the interesting questions lay elsewhere, in exoplanets, in dark energy, in the cosmic microwave background. The outer solar system was mapped, catalogued, and mentally filed away. Fan reopened the file by ignoring the assumption. He treated the data as data, without the interpretive layer that 4 decades of consensus had laid on top of it. He asked a simple question: did anything move? And the data answered. If his candidate is confirmed, the lesson will be uncomfortable. This is not because anyone made a mistake, but because the evidence was always there. It was not hidden by distance or faintness or technological limitation. It was hidden by the belief that there was nothing to find. That belief may have cost the field 40 years. On a mountain in northern Chile called Cerro Pachón, at an elevation of roughly 8,800 feet, a telescope is preparing to change the terms of the debate permanently. The Vera C. Rubin Observatory is named after the American astronomer who provided some of the most compelling observational evidence for dark matter in the 1970s. The telescope houses a primary mirror, 27.5 feet across. Its camera is the largest digital camera ever constructed for astronomy. It has 3.2 billion pixels. A single exposure covers an area of sky roughly 40 times the size of the full moon. The observatory's primary mission is called the Legacy Survey of Space and Time. Beginning in 2026, the telescope will photograph the entire visible southern sky every 3 nights. It will repeat this cycle for 10 years. Every patch of sky will be observed hundreds of times. Every object that moves will be catalogued. Every faint smudge that shifts position from one exposure to the next will be flagged and tracked. This is the instrument that the Planet 9 hypothesis has been waiting for, and perhaps dreading. The predicted orbital parameters place Planet 9 somewhere in a broad swath of sky. It would move slowly enough to appear nearly stationary over short timescales, but detectably different over months and years. Previous surveys have searched portions of this region without success, but previous surveys had limitations. They covered incomplete areas. They operated for limited durations. They reached certain depth thresholds, and no further. The Rubin Observatory will go deeper and wider and longer than anything before it. The Vera C. Rubin Observatory's method of repeatedly photographing the same sections of the sky means that signals from even profoundly faint, slow-moving bodies can build up over many observations. By stacking a sufficient number of these exposures, a dim point of light can be made to emerge from the background noise. It is projected that the observatory will successfully rule out approximately 84% of the remaining parameter space where Planet 9 might currently be concealed. If Planet 9 does exist, within the ranges of brightness, sky position, and orbital distance that contemporary models anticipate, the Rubin survey will detect it. This is not a guess, but a mathematical conclusion based on the survey's depth, its area of coverage, and its calculated detection probabilities. And should the observatory fail to find it, the consequences are just as profound. The lack of a detection after a comprehensive 10-year survey would not be definitive proof that Planet 9 does not exist. Instead, it would prove that Planet 9 does not exist where the prevailing models have placed it. This outcome would force a revision of the predicted orbits and a recalculation of the mass estimates. The entire hypothesis would come under a kind of observational pressure that no amount of statistical modeling alone could withstand. Some in the astronomical community have characterized the Rubin survey as the final chapter in this search. That particular framing may be a bit premature, as science rarely concludes with such clean finality. The observatory will, however, impose a firm deadline on a debate that has continued for nearly a decade without a clear resolution. The data is coming. The object will either materialize in the images, or it will not. The mountain in Chile is prepared. The immense mirror is polished to perfection. The camera has been installed. The software pipelines, designed to process terabytes of information each night, are undergoing final testing and refinement. The moment of first light is drawing near. Following 20 years of simulation, inference, and argument, the outer solar system is poised to be photographed with a completeness that will leave very few places for a world to remain hidden. There is a version of this narrative that does not conclude with a count of 9 planets. Some of the very same dynamical models that forecast a single, massive hidden planet also permit the existence of a second one. This concept has been investigated in several forms since the mid-2010s. The thinking is that while one distant, massive body can account for the orbital clustering of trans-Neptunian objects, certain refinements of the data hint that a lone planet may not fully explain every observed characteristic. The orbits of specific objects seem to resist this simple explanation. Even when Planet 9 is factored into the models, their inclinations remain too steep, or their perihelia are either too high or too low. Their orbital periods also fail to resonate with the predicted planet in the anticipated manner. One potential solution is the presence of a second undiscovered planet, informally known as Planet Y or Planet 10. This world would be smaller than Planet 9, perhaps 1 to 2 Earth masses, and would orbit closer to Sol, somewhere between 200 and 300 astronomical units away and in a different orbital plane. Its gravitational pull would be more subtle, and its influence on the trans-Neptunian population would overlap with Planet 9's in some areas, while diverging in others. The evidence for Planet Y is thin, certainly thinner than the evidence for Planet 9, which is itself a matter of debate. The models that generate a second planet often depend on very specific assumptions about the solar system's initial conditions. If these starting parameters are altered even slightly, the necessity for a second body tends to vanish. The statistical foundation is fragile, relying on a small sample of objects whose orbits are known to have large uncertainties. Yet the idea endures, sustained by a deeper historical pattern. Every single time astronomers have declared the solar system's inventory to be complete, they have been mistaken. William Herschel found Uranus in 1781, and for a short while, the solar system contained 7 planets, which seemed a sufficient number. Then came the discovery of Neptune in 1846, its existence predicted by mathematics before it was ever observed through a telescope. Pluto followed in 1930. The 1990s revealed the Kuiper Belt, a vast realm of thousands of icy bodies no one had previously imagined. Then Eris was spotted in 2005, a world larger than Pluto and situated even farther away, a complete surprise. Each of these discoveries compelled a revision of our cosmic map, and each revision showed that the previous version was incomplete. This pattern is so consistent it has almost taken on the quality of a natural law. The solar system is always larger, stranger, and more populated than the current generation of astronomers believes it to be. Planet Y may be purely speculative. It might become unnecessary once superior data arrives from the Vera C, Rubin Observatory, and other future infrared surveys. It could simply dissolve into statistical noise just as many theoretical predictions have in the past. But its presence in the models serves as a potent reminder that the map is not the territory, the catalogue is not the sky, and the assumption that we have found everything worth finding has been proven wrong every time it has been put to the test. The outer solar system is vast, stretching from Neptune's orbit all the way to the edge of our star's gravitational dominance, forming a sphere roughly 2 light-years in diameter. We have surveyed only a tiny fraction of this enormous volume, a thin slice near the ecliptic plane, and a few narrow, targeted searches in specific directions. The rest remains dark and unknown, possibly filled with objects we have not yet even learned how to search for. If Planet 9 is ever confirmed, the immediate question will be whether it is alone. History would suggest it is not. An object that should have settled the argument did the exact opposite. Discovered in 2017, the body they named Ammonite follows an orbit at a roughly 90-degree angle to every other extreme trans-Neptunian object in the sample. When the entire argument for Planet 9 is built upon orbital alignment, a body moving perpendicular to that alignment presents a significant problem. The question is, what kind of problem is it? Some researchers viewed Ammonite as a fatal blow to the hypothesis. They argued that if a massive unseen planet were corralling these distant objects into a common orbital plane, then a body at 90 degrees to that plane simply should not be there. Its existence implied that the clustering was just statistical noise or random scatter, the kind of illusory pattern that emerges when one searches for order in a small dataset. Others examined the very same orbit and arrived at the opposite conclusion. Their simulations demonstrated that a planet of about 5 Earth masses on an inclined, eccentric orbit would, over time, produce 2 distinct populations. One group would cluster near the planet's own orbital plane. The other group would be kicked into perpendicular orientations through a specific series of resonance interactions that play out over hundreds of millions of years. This perpendicular population would be smaller and more difficult to detect, but it should exist. In this interpretation, Ammonite is not a contradiction, but is instead powerful evidence for Planet 9. The very object that appears to be a counterexample becomes a fulfilled prediction. The trouble is that both of these interpretations hinge on Ammonite's orbit being accurately measured, and it is not. The object was only observed over a very short arc, based on a handful of detections spread across a few years. Based on this very limited information, astronomers inferred an orbital period stretching across thousands of years, along with an inclination that seemed to place the object in a distinctly perpendicular category. The challenge, however, is that short observational arcs yield highly uncertain orbits. Just a few more years of tracking could cause the calculated path to shift by tens of degrees. Its orbital inclination, for instance, could decrease significantly, and its semi-major axis could also change. The object that is currently measured at a 90 degrees angle might, with more precise data, slide closer to 60 or 110 degrees. Each of these outcomes tells a profoundly different story about the reality of Planet 9. This single icy body compresses the frustrating core of the entire debate into one object. The most critical member of the sample is also the one whose path is least understood. Every simulation that incorporates ammonite must treat its orbit as if it were reasonably well known. Every statistical analysis weighing the significance of the clustering has to assign it a position that could be incorrect by a very wide margin. And because the collection of extreme trans-Neptunian objects is so sparse, every individual member exerts an enormous influence. Repositioning just one of these objects can reshape the entire distribution. Tracking programs are continuing to monitor ammonite, and each new detection helps to tighten the orbital solution by a small fraction. By the late 2020s, the observational arc should be long enough to pin down its inclination to within a few degrees. That single measurement has the potential to flip the entire statistical argument in either direction. A confirmed perpendicular orbit would lend significant strength to the Planet 9 model, as the simulations predict the existence of exactly such a population. Conversely, an orbit that drifts back toward the main group of objects would weaken the perpendicular argument, returning the object to the aligned sample and thereby strengthening the clustering signal. An orbit that settles somewhere in between these two possibilities would offer no useful clarity at all. For the moment, ammonite exists in a kind of quantum state. It serves as both the most compelling evidence for Planet 9 and the most compelling evidence against it. The resolution to this paradox hinges on data that has not yet been collected. For nearly a decade, astronomers have been debating an object whose orbit they cannot yet definitively determine. The stakes are simply too high for anyone to be willing to wait in silence. Scientific papers continue to reference the 90 degrees inclination as if it were a settled fact, but it is not. The most consequential measurement in the science of the outer solar system is still being refined, one night at the telescope at a time. Every few years, a new exoplanet survey provides an updated census of the worlds orbiting other stars. While the specific numbers may shift slightly with each new data release, one particular finding has remained consistent for more than a decade. The most prevalent type of planet in our galaxy is a super-Earth, a world that is larger than our own but smaller than Neptune. Approximately 30% of stars similar to our Sun host at least one such planet, and some estimates place that number even higher. They are found in both tight and wide orbits, circling red dwarfs as well as stars nearly identical to our own. Super-Earths, it seems, are everywhere, yet our solar system does not have one. In the space between the inner rocky planets and the outer ice giants, there is a void. Earth represents one end of the mass spectrum for solid worlds, while Neptune occupies the other. The gap that separates them is a factor of 17 inches mass. In the majority of planetary systems observed by the Kepler telescope, this gap is filled, often with multiple planets. This absence in our own cosmic neighborhood is, from a statistical standpoint, quite strange. The existence of Planet 9 would neatly resolve this apparent anomaly. At an estimated 4 to 5 times the mass of Earth, it falls squarely into the super-Earth category. Its discovery would imply that our solar system did indeed form the same type of planet that nearly every other system seems to produce. We simply ended up with ours in a highly unusual location, having been flung into the distant reaches by a gravitational encounter with Jupiter or Saturn during the solar system's chaotic first 100 million years. In this scenario, the planet is real. It just migrated to an orbit so remote that the evidence of its existence went unnoticed until the 21st century. The alternative view is that our solar system genuinely lacks this class of world. This would mean that whatever process builds super-Earth so commonly in other systems either failed to operate here or operated in a different way. Such a conclusion would make our planetary system a true outlier among the thousands that have now been catalogued, an oddity that demands its own unique explanation. Planetary scientists would be faced with the challenge of understanding why the most common planetary assembly line in the galaxy seems to have skipped our star entirely. Both of these possibilities carry significant weight. If Planet 9 is confirmed, the solar system rejoins the cosmic majority. It becomes ordinary, a system composed of rocky planets, gas giants, ice giants, and a super-Earth. The only peculiarity is that the super-Earth happens to orbit at 500 astronomical units instead of 5. The formation models that successfully explain exoplanet populations would apply to us with only a minor adjustment. One ejection event, one unlucky gravitational kick during an early period of instability. Everything else would follow the standard template. If, however, Planet 9 does not exist, the question inverts, forcing us to ask why our system is so different. Why did the disk of gas and dust around the young sun produce Jupiter and Saturn, Uranus and Neptune, but completely skip the most common planetary mass range? The answer could lie in the specific timing of the giant planet's migration, the total mass of the original disk, or some interaction between Jupiter and the inner solar system that either prevented a super-Earth from forming or destroyed it. Each of these explanations is plausible, but none has been confirmed. The data from exoplanet studies creates a subtle but firm pressure on the Planet 9 hypothesis. The universe itself seems to suggest that super-Earths ought to be present. Finding one in our own system, even on a bizarre and distant orbit, would resolve a lingering statistical tension that has troubled planetary scientists since the first data release from the Kepler mission. It would signify that the processes that shaped our solar system were not unusual, that we are typical, and that the only strange feature is the orbit, something dynamical models can readily explain. An absence, on the other hand, would be more difficult to account for, and perhaps harder to accept for researchers who have spent their careers developing universal models of planet formation. For the first time in the history of this search, every competing hypothesis makes a distinct and testable prediction. This fact alone separates the current moment from all previous eras of speculation about a ninth planet. Percival Lowell could not design an observation that would distinguish his planet X from a mere statistical fluke. The observational tools of his time simply did not exist, and the predictions were not sharp enough. Today, they are. If a physical planet truly orbits at the predicted distance, the Vera Rubin Observatory will see it. The telescope survey is designed to cover the relevant strip of sky repeatedly over a period of 10 years. A planet of 4 to 5 Earth masses at a distance of 300 to 500 astronomical units would manifest as a faint point of light, moving slowly against the backdrop of distant stars. The movement of such a planet would be minimal, possibly just a few arc-seconds, but the survey's observational rhythm is engineered to identify precisely this type of slow-drifting object. A successful detection would hinge on linking together observations from several different nights while simultaneously filtering out the millions of asteroids and imaging artifacts present in every frame. The software pipelines have been specifically constructed for this immense task. If the planet exists and its location falls within the survey's footprint, the Rubin Observatory is expected to find it. The prediction, however, transforms entirely if the object is instead a primordial black hole. A black hole with 5 Earth masses would have a physical size comparable to a tennis ball. It gives off no light of its own and reflects none from the sunday. The only means of discovering it would be through the effects of gravitational lensing or by observing the infrequent flares it would generate when capturing and annihilating a small body from the Oort cloud. In the survey data, these flares would manifest as brief, transient events, shining brightly for a few hours or days before vanishing completely. This is a pattern quite unlike that of any known asteroid or variable star. The Rubin survey's fast cadence and expansive field of view make it exceptionally sensitive to these exact kinds of transient phenomena. A primordial black hole would therefore leave a signature in the data that bears no resemblance to a planet. If, on the other hand, modified gravity is the true explanation for the orbital clustering, then there would be no object to discover at all. The orbital alignment would simply persist in the Rubin data. The clustering signal would hold its statistical significance even as the collection of extreme trans-Neptunian objects expands from 24 to many hundreds. Yet, in this scenario, the survey would find neither a planet nor any characteristic flares. The gravitational anomaly would exist without an identifiable source. This particular outcome would be the most challenging to confirm, as it would necessitate proving a negative. It would require years of survey data that consistently show the clustering effect but fail to detect any causative object. Skeptics would likely contend that the planet is just dimmer than anticipated or located outside the survey's search area. At a certain point, however, the continued non-detection would itself become a powerful piece of evidence. The simplest prediction of all emerges if the clustering was merely a product of observational bias from the start. The Rubin survey scans the heavens with uniformity. It does not give preference to the specific regions where earlier telescopes happened to be aimed. As the sample size of distant objects increases under these unbiased conditions, the clustering signal would gradually dissolve. The orbital alignment that inspired 1,000 scientific papers would be revealed as an artifact of where astronomers had previously chosen to look. The distribution of orbits would become random. The Planet 9 hypothesis would then join Planet Vulcan and the canals of Mars in the historical archive of elegant concepts that were ultimately disproven by data. One telescope presents 4 distinct hypotheses, each with its own unique outcome. The crucial observations that will distinguish between them are already being gathered. The Rubin Observatory has achieved its first light and has now commenced its survey operations. Within just a few years, the resulting dataset will be substantial enough to test every prediction with a level of statistical confidence that leaves very little room for ambiguity. Michael Rowan Robinson's candidate object is located in an infrared catalogue compiled in the early 2000s. It was a faint source initially picked up by the 2-micron all-sky survey and was later cross-matched with the wide-field infrared survey explorer. Between those 2 separate observations, the source appeared to move approximately 47 arc-minutes over a span of 23 years. This rate of motion is consistent with an object situated between 200 and 500 astronomical units from our central star. This represents the correct distance and the right brightness for a body of several Earth masses residing at the distant edge of the solar system. The difficulty, however, is that infrared catalogues are notoriously messy. They are filled with millions of sources, including distant galaxies, brown dwarfs, detector artifacts, and cosmic ray impacts. Cross-matching between surveys that were conducted decades apart can introduce alignment errors. A faint galaxy that seems to have shifted its position slightly between different catalogue versions could easily mimic the apparent motion of a slow-moving object much closer to home. For any single source, the probability of such a false match is quite low. But when searching through millions of catalogue entries for objects that have the right motion and brightness, even a minimal false positive rate will inevitably generate some candidates. Rowan Robinson's analysis took this into account. The candidate object successfully passed through multiple filters that were designed to weed out galaxies and artifacts. Its colors were consistent with those of a cold, remote planetary body, not an extragalactic source. Its movement also fell squarely within the range that was predicted by the Batygin and Brown orbital models. The probability that a chance alignment could produce this specific combination of properties was calculated to be less than 1%. While this is encouraging, a 1% chance across such a massive catalogue still means that occasional false alarms are possible. In principle, the follow-up work is straightforward. The candidate's observed motion over 23 years allows for a precise prediction of where it should be in the sky in 2025. A modern infrared telescope aimed at that specific location ought to detect the object if it is real. If the telescope sees nothing, the candidate was most likely a catalogue artifact or a background galaxy whose apparent motion was just an illusion created by measurement error. But if an object does appear at the predicted position and with the predicted brightness, the case for its existence becomes very difficult to dismiss. Several research teams have already submitted requests for telescope time to carry out this exact observation. The specific details of this follow-up work remain partly under wraps due to the intense competition to be the first to either confirm or refute the candidate's existence. A positive detection would represent the most significant discovery in our solar system since the planet Neptune. A negative result, by contrast, would be little more than a footnote. This asymmetry in potential outcomes is what drives the sense of urgency. The deeper lesson here concerns scientific method. The data used in the analysis has been publicly available for many years. Thousands of astronomers had access to the very same catalogues. The technique of cross-matching infrared surveys to find slow-moving sources is not a new one. What was brought to the problem was patience and a very specific question. The research asked whether existing data might already hold the answer that everyone else assumed would require a brand new telescope. The approach feels almost retro. It involved no machine learning pipeline and no supercomputer simulations, just archival data and meticulous matching. There is a long and storied history in astronomy of major discoveries hiding in plain sight. The position of Neptune, for instance, was recorded on star charts decades before anyone realized it was a planet. Pluto appeared on photographic plates that were taken years before Clyde Tombaugh's official discovery. This pattern repeats because astronomers generate far more data than they can possibly analyze in real time. Archives grow, scientific questions evolve, and sometimes the solution to a new query is already waiting in an old dataset for someone to ask the right question. If this candidate proves to be real, the discovery will belong to someone who examined what was already there and saw what others had missed. It would be a cold case solved, not with new evidence, but with a fresh pair of eyes on old files. Percival Lowell was brilliant, wealthy, and obsessive. In the high desert of Arizona, Percival Lowell constructed an observatory for the specific purpose of studying Mars and discovering a planet beyond the orbit of Neptune. His mathematical argument for this so-called Planet X was notably elegant, based on the theory that observed disturbances in the orbital paths of Uranus and Neptune could reveal the location of a massive, unseen world. From these perturbations, he calculated where such a body should be, subsequently publishing coordinates and directing extensive photographic surveys. The final decade of his life was dedicated to this search, but his conclusion was ultimately incorrect. The orbital irregularities he had measured were, in fact, contained within the statistical noise of his data. The planet he predicted simply did not exist at that location, or with the mass he had proposed. 14 years after Lowell's death, Clyde Tombaugh found Pluto in 1930, near the sky region Lowell had identified. For many decades, this discovery appeared to be a vindication of his work, suggesting his mathematics had been proven right after all. An intriguing detail, however, was that Pluto was far too small to have created the gravitational effects Lowell had recorded. The discovery was ultimately a profound coincidence. Pluto just happened to occupy roughly the right area of the sky for reasons entirely unconnected to his theory. The mathematical foundation upon which his prediction was built had relied on measurements that were fundamentally flawed. This history casts an uncomfortable shadow over the current search for a new planet. Konstantin Batygin and Mike Brown are brilliant, well-resourced, and deeply invested researchers. Their mathematical prediction for what they call Planet 9 is similarly elegant. After observing an unusual clustering in the orbits of extreme trans-Neptunian objects, they calculated where a large, hidden world ought to be. They have published its potential orbital parameters and have also directed observational surveys to find it. Their search has now been ongoing for nearly a decade. The method they employ is the very same one that Urbain Le Verrier used in 1846. First, an anomaly is observed in the motion of known celestial bodies. Then, an assumption is made that this anomaly is being caused by the gravity of an unseen mass. Next, calculations determine the position that mass must occupy. Finally, a telescope is pointed toward that calculated spot. Le Verrier's prediction led directly to the discovery of Neptune on the very first night of looking. This particular method yielded one of the greatest triumphs in the history of mathematical astronomy, yet it also produced Percival Lowell's long years of fruitless searching. The question that hangs over the present-day search is which of these precedents will apply. Is our current era more akin to 1846, when the math was correct and the planet was real? Or is it more like 1906, when the math was sophisticated but the planet was imaginary? The superficial parallels between the work of Batygin and Brown and that of Le Verrier are obvious and frequently pointed out. The surface similarities to Lowell's work, however, are mentioned less often. Both endeavors use gravitational perturbations to infer the existence of an unseen world. Both produced specific, testable predictions about its location, and both involved extensive searches that, at the time of their most confident publications, had not yet succeeded in finding the predicted object. But the differences between these cases matter a great deal. Le Verrier worked with precise measurements of a single planet's position gathered over decades. Lowell, by contrast, worked with noisy measurements, which were later understood to contain systematic errors. Batygin and Brown are working with a statistical pattern found within a small sample of distant objects, whose orbits are themselves not known with perfect certainty. It is the quality of the initial data that determines if a mathematical framework will produce a truth or an illusion. And the quality of the input data for the Planet 9 hypothesis is still a matter of genuine scientific dispute. The uncomfortable truth is that a methodology, by itself, cannot tell you in advance if it is going to succeed. Leverrier's approach was identical to Lowell's, yet their outcomes were complete opposites. The crucial variable was not the mathematics being used, but the data that was feeding into that mathematics. And whether the data supporting Planet 9 is clean enough to lead to a Leverrier-style outcome, or noisy enough to produce a Lowell-style outcome, is the question at the heart of the matter. This is a question that no amount of historical comparison can resolve. Only a telescope aimed at the correct patch of sky can ever settle it. History does not repeat itself in astronomy any more than it does in other parts of life. But it does rhyme often enough that making confident predictions can be a dangerous game. On the night of September 23rd, 1846, Johann Gottfried Galle pointed the 9-inch refractor at the Berlin Observatory toward coordinates that had been provided in a letter from Urbain Le Verrier. Within a single degree of the predicted position, Galle and his student, Heinrich de Rest, spotted a faint point of light that did not appear on their star chart. They watched it for several hours and saw that it moved. It was Neptune. The discovery required only a single night. What stands out is that Le Verrier had never once looked through a telescope to find it. His work was conducted entirely with pen and paper. The planet Uranus was not following the precise orbit that Newtonian gravity said it should. The deviations from this path were small, yet they were precise. Le Verrier made the assumption that an unseen planet was pulling Uranus slightly off its course. He then spent months performing calculations to determine where that planet must be to cause the exact deviations being observed. He sent his resulting coordinates to Galle. Galle looked, and the planet was there. This remains the single most spectacular demonstration of mathematical prediction in the history of planetary science. Nothing before or since has ever matched it for its sheer precision and immediacy. The event created a template, a kind of blueprint that every planet hunter since has tried to follow. An unseen mass causes an observable perturbation. Mathematics then reveals the location of that mass. A telescope confirms the result. The method worked so perfectly for Neptune that it quickly became the default approach for finding anything hidden in the solar system. Percival Lowell followed this template to the letter. He measured what he believed were perturbations in the orbits of Uranus and Neptune. He calculated, he predicted, and he searched, but he failed. The perturbations he had based his work on were not real. The planet he predicted did not exist with the properties he had described. The template that had been so brilliantly successful in 1846 failed completely in 1906. Today, Batygin and Brown are following that same template once again. They observe an anomaly, they calculate, and they predict. The key difference between their work and Le Verrier's is found in the nature of the input signal itself. Le Verrier had access to decades of precise positional measurements of Uranus. Each data point was a direct measurement of where the planet was in the sky at a known time, making the signal clean and the perturbation unambiguous. The mathematical inversion from that perturbation to the planet was therefore well constrained. Batygin and Brown have something different. They possess a statistical clustering in the orbital elements of roughly 24 distant objects. Each individual object's orbit is itself uncertain. The clustering they see may be real, or it could be an artifact of where telescopes have happened to look. Their signal is not a precise wobble in a single planet's path. It is a pattern in the distribution of a small sample of bodies. The mathematical framework that connects this pattern to a planet is sophisticated, but the input is far noisier than what Le Verrier had to work with. This single distinction determines everything. If the clustering is real and unbiased, the mathematical prediction should lead to a planet, just as Le Verrier's did. If the clustering is partly or wholly an artifact, then the prediction leads nowhere, just as Lowell's did. The underlying method is fundamentally sound, having been thoroughly tested and proven to work, provided the input data is clean. The pivotal open question is whether the data pertaining to Planet 9 actually meets that essential standard. The precedent established in 1846 relies on a single condition that no degree of mathematical elegance can replace. The anomaly under investigation must be genuine. So far, an estimated 84% of the possible parameter space for Planet 9 has been ruled out. A series of surveys, each covering different portions of the sky at various depths, has systematically eliminated the regions where such a planet could be hiding. To an outside observer, this might sound like terrible news for the hypothesis. The logic seems simple. If you have searched 84% of a haystack and failed to find the needle probably isn't there. This framing, however, misunderstands the mechanics of the search. The 84% of possibilities that have been discounted are composed of the scenarios in which Planet 9 would be at its closest, its brightest, and therefore its easiest to detect. A planet with a mass of 6 Earths located 200 astronomical units away would have been found many years ago. Likewise, a world at 300 astronomical units on a low-inclination orbit in the northern sky would have been captured in data from the Panoramic Survey Telescope and Rapid Response System. These more straightforward cases are now off the table. What remains is the 16% that contains the most difficult scenarios. This is the realm of a planet orbiting between 400 and 500 astronomical units. It is a world with a mass perhaps closer to 4 Earths rather than 6. It could be an orbit that currently places it in a region of the sky contaminated by the dense star fields of the Milky Way's galactic plane. Or it might be a specific combination of distance, mass, and position that leaves it just beneath the detection threshold of every single survey conducted to this point. These are the scenarios that endure, precisely because they represent the greatest challenge to test. Interestingly, the continued non-detection has accomplished something that a discovery would not have. It has significantly sharpened the prediction. Each survey that comes up empty removes another slice of the parameter space. Consequently, the remaining viable region begins to shrink. The predicted mass range tightens, and the possible distances narrow. The planet's potential position on the sky becomes more and more constrained. The result is a quiet paradox. A planet that has not been found is now better characterized than it was when the search first began. The boundaries drawn by its absence are remarkably precise. This follows the classic pattern for any search that approaches its target asymptotically. The initial surveys eliminate the easy possibilities very quickly, making progress feel rapid. Then, the search slows as the remaining parameter space is composed only of the hardest cases. Each subsequent survey eliminates a smaller portion than the one before it. The search enters a phase where immense effort yields only incremental gains. This is precisely where the hunt for Planet 9 currently resides. The Vera Rubin Observatory fundamentally changes this calculus, as it can reach deeper across a wider field than any previous survey. It provides access to portions of that remaining 16% that no prior instrument was capable of touching. Whether it can survey all of it remains uncertain. A planet at 500 astronomical units, with a mass of 4 Earths, sitting at the faintest end of the predictions, might still evade detection even after a full decade of Rubin data. The search would then simply continue, passed on to the next generation of telescopes, and then the generation after that. There is a psychological dimension to consider as well. A decade of finding nothing can wear on the scientific community. Funding agencies begin to ask if continued searches are truly justified. Telescope allocation committees must weigh proposals for Planet 9 against other compelling science. Skeptics point to the empty results, arguing that the hypothesis has been given its chance. In response, supporters counter that the remaining parameter space is exactly where a real planet would be expected to hide. This debate unfolds not just in journal pages, but also in proposal reviews and conference hallways. The 84% figure is not a sign of failure. It is a map of where the planet is not. And that map, through a process of elimination, points with increasing focus toward where it might be, the most distant, faintest, and most difficult corner of the search space. This is exactly the kind of place where a world could have remained hidden for the entire history of telescopic astronomy, completely unnoticed. Stepping back from the individual arguments to look at the accumulated evidence reveals a complex picture. Sedna was discovered in 2003, following an orbit so extreme that nothing in the known solar system could account for it. A decade later, 2012 VP 113 was found on a similarly inexplicable path. Then came the Goblin, 2015 TG 387, which extended the pattern even further. Today, more than 20 extreme trans-Neptunian objects have been catalogued, all with orbits that reach hundreds of astronomical units from our central star. The announcement in 2016 of a clustering in these orbits suggested a common gravitational influence. From these orbital dynamics, a mass of 4.4 Earths was inferred. There is also the matter of an IRAS candidate from 1983 that was dismissed as a galaxy, but might, in retrospect, have been the planet all along. We have the case of Ammonite, an object flying at 90 degrees to the main cluster, which either destroys the hypothesis or confirms one of its subtle predictions, depending on which simulation one trusts. A primordial black hole hypothesis has been proposed, which is physically possible but nearly impossible to test. There is also a modified gravity explanation that would remove the need for any object at all. A Planet Y hypothesis suggests that if one hidden world exists, others might as well. And now, the Vera Rubin Observatory is surveying the sky with a sensitivity that none of its predecessors could ever match. This is not a case with too little evidence. It is a case with too much. Each new discovery over the past 2 decades has made the mystery stranger rather than simpler. Sedna should have pointed directly to Planet 9 if its orbit were well understood, but instead, it just opened a new question. VP 113 should have narrowed the field of possibilities, but instead, it doubled the puzzle. The clustering signal should have been either confirmed or refuted by now, yet it remains in a statistical grey zone that allows both believers and skeptics to claim support. The IRAS candidate could have resolved everything 40 years ago, if only someone had followed up before the source moved out of the survey frame. Ammonite could resolve everything now, if its orbit were measured with enough precision to place it firmly in one population or another. The Fan candidate could resolve everything within months, if follow-up observations find a moving object at the predicted coordinates. Every piece of evidence points somewhere, but the problem is that they do not all point in the same direction. Some clues favor a planet, while others favor observational bias, and still others suggest something stranger than either. The map of clues looks less like a trail leading to a single conclusion and more like a web of partial connections that resists simplification. The situation resembles a detective case, where every new witness adds a contradiction instead of a confirmation. The physical evidence is real, the orbits are measured, and the objects exist. What remains uncertain is the story that connects them all. The alignment of these distant objects could be explained by a single gravitational source, but it could just as easily be a product of observational bias combined with simple coincidence. It might also point to a form of physics that has not yet been conceived. After 20 years of discovery, dozens of scientific papers, and thousands of hours of telescope time, we are left with multiple competing hypotheses. Each one is internally consistent, and each accounts for some of the evidence while failing to address the rest. The central question, first raised by the discovery of Sedna, remains precisely as it was. A fundamental discrepancy seems to exist in the far reaches of our solar system, and we do not yet know its cause. The body of evidence has certainly grown, but the mystery itself has not diminished. We have sent spacecraft to every known planet in our solar system. Orbiters have circled Mercury, Venus, Mars, Jupiter, and Saturn. Probes have performed flybys of Uranus and Neptune, capturing detailed imagery as they passed. We have achieved a landing on a comet, made contact with the surface of an asteroid, and brought samples back to Earth. We have even photographed the nitrogen glaciers on Pluto from a distance of just 7,000 meters. By any standard, this initial reconnaissance of the known solar system stands as one of the great accomplishments of our species. And yet, it is possible that a planet 4 times the mass of Earth is currently orbiting our star, completing a single circuit every 10 to 20,000 years. This world would be massive enough to tilt the orbital plane of the entire outer solar system by 6 degrees. It would be substantial enough to shepherd 24 smaller bodies into strangely aligned orbits. It would be large enough to be classified as the 5th largest planet, but we have no clear idea where it is, or even if it truly exists. The fundamental challenge is one of immense distance. Beyond 100 astronomical units, the solar system is effectively unexplored territory. Voyager 1, the most distant object ever made by humans, is now about 163 astronomical units from its home star after nearly 5 decades of travel. It has journeyed through that enormous space without encountering anything significant, but Voyager's trajectory is just a single, thin thread passing through a colossal volume of space. The region between 100 and 1,000 astronomical units from the star is vast, containing millions of times the volume of the inner solar system. A planet located at 400 astronomical units could remain there for billions of years without a single spacecraft ever passing within a billion miles of it. The curious truth is that we possess better maps of galaxies millions of light years away than we do of our own cosmic backyard at these scales. The Hubble Space Telescope has produced images of galaxies at the very edge of the observable universe with extraordinary detail. The James Webb Space Telescope is peering into stellar nurseries thousands of light years from us. We can determine the chemical composition of atmospheres on planets that orbit other stars. We can count the craters on the moons of Jupiter from our own orbit around Earth. Our technology for observing distant objects is remarkable. However, the technology for seeing faint objects nearby is a different challenge, and one that has been less developed. A world at 400 astronomical units would be exceedingly faint, a consequence of its cold temperature and the fact that the starlight it reflects diminishes to the 4th power of its distance. If you double the distance, the reflected light decreases by a factor of 16. At 500 astronomical units, a planet the size of a super-Earth would be dimmer than magnitude 26. Such an object would be visible only to the largest telescopes on Earth, and only then with long exposures and meticulous image processing. It would be lost within the background noise of faraway galaxies and the detector artifacts that appear in every deep sky image. The outer solar system is not concealing this potential planet through any exotic means. There is no cloaking device at play, no unusual physics involved. The planet, if it is out there, is simply too distant and too dim for the surveys that have been conducted so far. The very same laws of physics that enabled New Horizons to photograph Pluto in such exquisite detail also guarantee that an object 20 times farther away will be millions of times more difficult to detect from Earth. Our inability to see is a direct consequence of this immense distance, a darkness that deepens exponentially to the 4th power. If Planet 9 is real, then every textbook diagram of the solar system published over the last 400 years is incorrect. Every model that assumed 8 planets was the complete inventory has missed a major component. Every simulation of solar system dynamics that failed to include a 5 Earth mass body in a distant, eccentric orbit was fundamentally incomplete. The 6-degree tilt of the solar plane, a feature that astronomers have long noted but never fully explained, was a signpost that everyone simply walked past. For the entire history of telescopic astronomy, from Galileo onward, a world larger than our own has been orbiting the star, and nobody knew. Conversely, if Planet 9 is not real, then 2 centuries of mathematical planet hunting have yielded a pattern of failure, interrupted by only a single success. Leverrier found Neptune. Everyone since has found nothing. Lowell's Planet X, the various trans-Neptunian planets of the mid-20th century, the different Planet 10 hypotheses of the 1980s, and now Batygin and Brown's Planet 9, each generation has approached the problem with better mathematics and more powerful telescopes. Each generation was certain of its conclusions. The clustering seen in the extreme trans-Neptunian orbits would then join the canals of Mars and the luminiferous ether as patterns that intelligent people were convinced they saw, but which turned out to be artifacts of imperfect observation and wishful interpretation. Either outcome is unsettling to our foundations. A discovered planet would rewrite the very architecture of the solar system and immediately raise questions about what else might be hiding in the darkness beyond Neptune. A confirmed absence would force a reckoning with how easily statistical patterns in small data sets can mislead even the most careful of researchers. Surveys are now underway at the Vera Rubin Observatory, with its data accumulating each night. Somewhere in that growing archive, the answer either exists as a faint, moving point of light, or it does not exist, its absence a conspicuous void. The fan candidate will be followed up using modern infrared telescopes pointed at its predicted position for 2025. Within months, it will either be confirmed as a moving object or dismissed as a ghost in the catalogue. The orbit of Ammonite will be refined with each new observation, and in a few years, its inclination will be determined precisely enough to test the perpendicular population prediction. The necessary tools are in place, and the observations are in progress. The timeline is short, at least by astronomical standards, perhaps 5 years, maybe 10. That is enough time for Rubin to complete its first full survey pass, and for the sample of extreme trans-Neptunian objects to grow from 24 to hundreds. And yet, every generation of planet hunters has believed it was the one that would finally resolve the question. Leverrier believed it. Tombaugh believed it. The astronomers who searched for Planet X through the 1970s and 80s believed it. A certainty about an imminent answer has been the one constant in a search defined by its failure to provide one. The ninth planet remains the oldest open case in all of planetary science. This single line of inquiry has remained open since 1846, outlasting the discovery of Neptune, the reclassification of Pluto, and digital surveys cataloguing thousands of exoplanets. It will likely persist beyond the Vera-Rubin Observatory as well. While future telescopes will bring greater sensitivity and sharper statistical tests on larger samples, the core question seems to always remain, waiting at the edge of our vision, just beyond the reach of our finest current instruments.